Okay, welcome everybody to this session of the ABC One World seminar. We're very pleased today to have Veronica Rockover as our speaker, and her affiliation is on her first slide here. So I will hand over to Veronica to start her talk.
Thank you so much for the introduction and for the invitation. It's really a great honor. Just one disclaimer, this talk is not about ABC. So even though this is an ABC seminar series, my talk is not necessarily about ABC, but it's about likelihood-free Bayesian inference. So I hope that, the departure from the kind of main topic of the seminar series is not going to be overly disappointing. So Metropolis-Hastings via classification. I like to introduce this talk with kind of a metaphor. It's an old classic with a new twist. We thought about sort of ways of performing Bayesian computation using machine learning, so turning optimization to a sampling. So this is one example of such a strategy. And this is a joint work with my colleague Tetsuya Kaji, who is faculty in the econometrics group at Booth. Okay, so the setup is fairly straightforward. I don't think I have to make a lot of notational introductions for this crowd, but for the sake of completeness, just let me lay down the actual statistical framework. So we are assuming an IID experiment where the true data comes from some parametric family indexed by parameter theta naught that we do not know, we want to estimate. And Bayesian inference can be made more complicated if we cannot evaluate the likelihood function. So the likelihood is somewhat important. We can all agree on that. And if we cannot evaluate the likelihood function, computations, including Metropolis-Hastings, are hampered because we just need to be able to evaluate likelihood ratios. So in such instances, of course, there is technology, and I have a review of those methodological developments on the next few slides. But I just want to point out that we are focusing on a situation where we have sort of parametric family, we cannot evaluate the likelihood function, or it's too costly to evaluate, and we want to perform Bayesian inference in this parametric setting. Examples of models where the likelihood is too costly to evaluate are very, prevalent. I have 3 examples at the bottom of the slide. One of them is the Heston models, stochastic volatility modeling. I will have example of the CIR model, which is kind of a part of a Heston model later on as an illustration, and also have illustration using the Vodka Volterra model, which is kind of quintessential example of sort of likelihood-free modeling. So those are the 2 examples I will cover later on. But you could think of any sort of hierarchical model where the latent variables, after integrating out, yield sort of intractable, where the marginal likelihood simply cannot be easily computed. The integration is just too difficult. So you can, there's a wealth of examples as well, including that random effects models and things like that. So what can we do? So here is the ABC slide. That's the only ABC slide I actually have. No, I have actually more. I have comparisons later on. But ABC is, I think, one of the most brilliant ideas in Bayesian computation over the last a long time. The idea is fairly straightforward, and it's based on the premise that if we cannot evaluate the likelihood, maybe we can simulate from it. So what we do is we simulate pairs of parameter values and simulated data, and then we keep the pairs which give simulated data, which have high fidelity to observed data, and that's measured by comparing summary statistics. So we simulate fake data, we distill information into summary statistic S, and we compare the summary statistic to the true data, and then if the summary statistics are close, we keep that sample. So it's a brilliant concept which allows parallel computation. I do have some sort of phonies here, just because I like to sometimes give you the pluses and minuses. I guess that this crowd also knows certain disadvantages of ABC. One of them is reliance on summary statistics. That has been somewhat automated using different measures of distance, maybe Kullback-Leibler or Wasserstein distances. between the fake and observed data using classification as well. So we have people working in this area on the call today. So I typically do not list too many references. I do not make exhaustive literature review on my slides, but obviously there has been a tremendous amount of work in that area. One disadvantage of ABC that I've kind of seen is that we're wasting too much information sampling from sort of uniform priors. So if the prior is kind of very vague, we're going to be wasting a lot of samples. And that's just the nature of the game, but it can be parallelized, so that's a good thing. So our idea here is somewhat related to ABC. We're going to be also simulating fake data, comparing them to true data through classification. So there has been a nice paper by Michael Gutman and co-authors using sort of classification inside ABC. We are kind of using classification inside Metropolis-Hastings to estimate likelihood ratios. So we are kind of inspired by the idea of simulating as opposed to simulating fake data to obtain estimator of the likelihood ratio. So our approach is kind of in between, like ABC, it's vaguely related, but it's really Metropolis-Hastings. And in Metropolis-Hastings, we have to compute the likelihood. And if you don't have access to it, maybe we can approximate it. So plug in approximations to likelihood function inside Metropolis-Hastings. That's also pretty, I don't want to say obvious, but it has been done. People have deployed estimators inside Metropolis-Hastings. Sometimes that's called the pseudo-marginal methods. Now the question is, how do we obtain those estimators? So one way would be, okay, well, we can maybe, if we have a latent variable framework, maybe we can perform some sort of integration by sampling from the latent variables inside of the hierarchical model, and that's what I call a pseudo-marginal technique. Or we could construct a kind of a proxy likelihood using summarized statistics. So if we have access to some reasonable summarized statistics, we can assume Gaussianity of those and then plug them in, and that's called a synthetic likelihood. So again, perhaps one disadvantage of synthetic likelihood would be the reliance on summarized statistics. Sometimes they're obvious, sometimes they're not obvious. So obviously, we can find examples where summarized statistics are not readily available, and in these situations, performing ABC using summarized statistics or synthetic likelihood will be perhaps not the most ideal, but we can also think of examples where this method might work really well. So our approach does not rely on summarized statistics. We will be deploying certain estimators of the likelihood ratio based on classification. What we also found is that the pseudo-marginal method may not be applicable in situations where we don't have the hierarchical latent variable model. So that really relies on the kind of integration of the latent variables. And we have to be able to sample from conditionals of those latent variables. And to obtain accurate estimators of the likelihood, maybe we need to simulate a lot of latent variables. So there's definitely going to be maybe computational sort of, I don't want to say difficulties, but it may take some time to be able to obtain a well-working pseudo-marginal due to the fact that we may need a lot of samples. And also there's versions of pseudo-marginal Metropolis-Hastings which may not necessarily yield the correct stationary distribution. So if you plug in an estimator of the likelihood, that may change actually the stationary distribution. And that's also something that we have been aware of in our approach. Okay, so our approach is fairly straightforward. It's basically the classic Metropolis-Hastings, right, where we have the likelihood ratios evaluated at a proposed value, which comes from some proposal distribution. And then we're just comparing the kind of like posterior ratios. And in order to deploy Metropolis-Hastings, obviously we need to be able to compute these likelihood ratios. The new twist on the old classic is the deployment of sort of classification-based likelihood ratios. So since I've been giving this talk with the last few months, people have every single time I get new kind of feedback, I get new kind of references, and it's this idea of performing sort of likelihood ratio estimation using classification has been quite popular in machine learning these days. So there's a lot of references in machine learning where that are somewhat related our approach, but we believe that this is kind of a rigorous treatment of a particular kind of simpler, just a very simple algorithm where we've taken somewhat kind of theoretical point of view as well, and we were able to understand the trade-offs of sort of variance trade-offs, taking certain sort of theoretical considerations. So anyway, so how does this work? So we want to estimate the likelihood ratio, and we're going to do that using the idea of sampling fake data. So we will sample fake data, compare them to real data, and from that we will obtain likelihood ratios. So that's kind of a looks perhaps, if you're not familiar with that kind of likelihood ratio trick that people refer to, let me just motivate it using sort of reference to a popular machine learning algorithm called GANs. So GANs have been very say popular in generating samples from distributions over complex objects such as images. And the way it works is that we train a machine which is two players, G and D generator, say a generator and a discriminator. So and the way it works is that these two machines kind of play a game against each other. The generator tries to deceive the discriminator by providing fake data which look alike the observed data, and the discriminator is going to try to discriminate between them. So the discriminator is some sort of estimate some sort of a function between 0 and 1 for real data and 0 for fake data, and the generator is generating these fake data sets. And this is a kind of like a minimax game where at the equilibrium the generator can no longer tell, and that's why the discriminator can no longer tell, and that's why the generator has been trained to produce realistic samples. So that's kind of a very compelling idea, and of course it relates to somewhat to ABC, and I was kind of fascinated by the possibility of converting GANs to posterior samples. So this is obviously sampling from the likelihood, we will sample from the posterior, so it's a different kind of concept, but I like to think that there's still some sort of a connection to be made. So to take the first step, we've kind of looked at this minimax game and just forget about the necessarily minimization here, and we just look at the classification part of that using this cross entropy loss. And we will have a kind of not a minimax game, but we will have just a basically max problem, not min-max problem. But anyway, so you have seen pictures of GANs outputs. So this is a collection of 6 samples sampled from a likelihood simulator trained on celebrity faces. Of course, none of these are real, but they look real. And we thought, well, maybe there is a better use for GANs than just generating pretty faces. And this is kind of a motivation for our talk. So obviously the GAN technology relies on a good classifier and a good discriminator. Those are typically deep learning networks. If you fail to have a really good discriminator or classifier, you may end up having a GAN, which may not be necessarily ideal. So this is an attempt to train a GAN for generating pictures of Veronicas. So some of these are real, some of these are fake. Obviously, we need to be a little bit careful when it comes to training GANs, because it's a very elaborate process in which you have to be able to distinguish between the real images and the fake images, such as chihuahuas and muffins. So I just like to make these kind of connections to GANs, even though this paper is not necessarily about GANs, but there is definitely aspects of it which relate to it. And the aspect is the generator. So we are going to be generating the fake data using the following idea. So there is some sort of latent variables, x tilde, which we pass through deterministic mapping, which depends on our parameter of interest. And that kind of filtering through the mapping will produce samples from the distribution indexed by theta. So this cartoon has been actually taken from the GAN paper nicely illustrates the generating process where we have the latent variables x tilde. Here we would have the deterministic mapping, which can transport the observations to certain areas, depending on the value of theta. If the value of theta is close to the truth is denoted by the green line here. We're going to obtain samples which kind of are very reminiscent of the observed data, in which the distributions will agree completely, and in which case the discriminator, being a function between 0 and 1, will be at, say, will be flat, because in that case the discriminator can no longer tell. But if you have sort of some parameter value which is a little bit outside of the range, I actually want to make a correction. The green is the generated distribution, and the black is the true distribution. So if we have a parameter value which is kind of far away, then we will obtain distributions which do not overlap, in which case there is opportunity for the discriminator to be able to tell, assigning 1 to the areas which are more in line with the real data, and then 0 to the area which is more in line with the fake data. So this is how it works. So we're going to be generating these fake data using this principle. And we're going to consider actually 2 alternatives where the latent variables x tilde are kind of fixed throughout the algorithm, and one alternative where they are refreshed. So we will consider these 2 alternatives which yield different stationary distributions, and there are certain bias variance trade-offs associated with these kind of random versus fixed variants. All right, so let's just talk about more mathematically how do we obtain those likelihood ratios. So this is the cross entropy loss empirical version of it. A few slides back we had the minimax game. Now we have the max game only, so it's not really a game, it's just a maximization, where we have a class of discriminators such as deep learning, logistic regression, whatever class you want to consider. And we want to discriminate, we want to distinguish between the generated data obtained from the discriminator and the real data, xi. So the xi tilde, every time I use tilde, I'm referring to the fake data. So, and also this should be an open interval. So anyway, that's just a little typo. So if you look at this maximization problem, it's known that the oracle discriminator, so the best classifier we can get is the kind of likelihood ratio classifier, which depends on the true value of theta, being theta naught. So this would be the optimal classifier for solving this kind of a problem. But obviously we don't have access to theta naught, so we cannot really, attain this oracle discriminator. But we can perhaps estimate it, and we can get close to it. So the trick here, the likelihood ratio trick that people refer to is the following. We basically shuffle things around here and write the likelihood in terms of the actual true likelihood. So here I have this is likelihood for one observation. We turn it into likelihood of the entire data. So there's the n here, and then we just kind of shuffle the terms around, and we can write the likelihood as a function of the sort of theta naught, right, times this exponential quantity, which depends on the oracle discriminator. So this quantity, as we know, it cannot be, we don't know it, but we might be able to estimate it. So the likelihood estimator, quote unquote, is obtained by replacing this oracle discriminator by its estimator. So by the oracle, yes, by the oracle discriminator by the estimator, obtained by just plugging in or solving this problem. So you may argue, well, this is not really an estimator because it depends on the unknown. So we like to think that in Metropolis-Hastings, this could be regarded as a constant which cancels out. So if you look at likelihood ratios, this is going to cancel out. So all we have to compute is this quantity, which depends on the discriminator. So that's kind of the key. So it's a kind of estimator, but what we are really after is the estimator of the likelihood ratio, in which case the quantity here is disappearing. Okay, so let's just kind of distill these two, the slide one more time. So we are turning the likelihood function into like a quantity which depends on the discriminator. We can now take this guy and then write it as a function of this guy, and we can plug it into this equation, and then we obtain the following. So it turns out that the estimator can be written as the original likelihood times exponential tilt, which depends on the kind of like almost a distance between the oracle discriminator and the estimator. So the likelihood function that we are kind of going to be plugging into the Metropolis-Hastings is basically proportional to the likelihood function, but it's exponentially tilted. And the amount of tilt depends on the quality of the discriminator, measured by this quantity U, which we analyze theoretically. And obviously, this exponential tilting is going to, affect the stationary distribution. So we were kind of obsessed in understanding how much it's going to affect the location and the spread, whether there is any hope to get a stationary distribution whose limiting shape is the same as the limiting shape of the original posterior distribution. So we spent a lot of time trying to understand theoretically the implications of this exponential tilt. And to that end, we considered two versions of the algorithm in which we fixed the latent variables and then we refresh them. So we refer to these as fixed and random. In the fixed case, what we do is traditionally just propose a new value of the parameter, generate our fake data by passing the latent variables x tilde through the deterministic mapping, and then just running the classification algorithm, obtain d hat, plug it into the expression for the estimator of the likelihood, and then we are off and running, right? So in this case, it's easy to see that the stationary distribution will be the actual posterior that we are after times the exponential tilt, right? So this exponential tilt is, it's not going anywhere. It's going to affect the location. We know that for Gaussian distribution, exponential tilt affects the location, right? And depending on the whether this function is linear or quadratic in theta, it's going to affect location and spread. So we know that this is, we are not really after necessarily the correct stationary distribution. That's something that has been also seen for some variants of the pseudo-marginal method. So we were not overly concerned, because if this approximation is good enough, then maybe we can just take it as an approximation, and maybe we can even obtain something reasonable. But we were kind of a little bit concerned about this. So we considered a second version of the algorithm called the random generator, where we refresh the latent variables x tilde at each step, in which case it's like we could consider this as a joint Metropolis-Hastings sampling from theta and x tilde jointly. So the only difference is really just refreshing the x tilde. And it's easy to see that the stationary distribution is again the posterior we are after, exponential tilted, but now the exponential tilt is averaged out. So it's kind of averaged out over distribution of the latent variables. And there is hope that this averaged out tilt is going to be, say, is going to be smaller. So if you average it out over a certain distribution, like still there's hope that this averaging out is gonna diminish the bias, and that's what we've seen in some of our simulated examples, that's indeed the case. So we like to think that there are two versions of this algorithm. One of them which will be after perhaps a correct shape and maybe not so correct location. So if our quantity u of theta here is linear in theta, the fixed generator will have some bias, but we can show that it will have the limiting shape is going to have the correct variance. So the shape will be, can be conceived to be right, but the location will be sort of perhaps not right. And in the second version, we like to think that perhaps due to the averaging aspect, the variance might be increased, but the bias might be diminished. So we kind of played around with these two alternatives, and we came up with kind of a combination of the two. So if we were not happy with running the algorithm 1 only, then we can maybe refine it by debiasing its samples by shifting the samples to, say, a mean of the algorithm 2. So there's a way of kind of refining the samples taking advantage of the strengths of the two to obtain samples, which under some assumptions will be from a distribution whose limiting shape is the same as the limiting shape of the actual posterior. So we kind of thought about theoretically understanding the situations when that happens. So
Veronica, sorry to interrupt. There's a question in the chat. Would you prefer to answer it now or leave it until the end?
If you don't mind reading it out loud for me.
Sure. Okay. So it's a question from Umberto Piccini, and he asks, how about correlating the pseudo-random draws between iterations, as in correlated pseudo-marginal Metropolis-Hastings?
Yes.
So you would reduce the variance of the acceptance ratio.
Right. That's a brilliant suggestion. So we are aware of that technique. We know that it's been successful at reducing variance. We may have implemented it, but we haven't really gone as far as really understanding how that would affect this kind of bias variance trade-off. So that would be something to consider in the future. But that could be a great extension. So I don't have any kind of theoretical insights right now, but we may have implemented it on some examples. But I don't recall exactly what the conclusion was, but definitely something to consider. Okay, so let's just talk a little bit more about the sufficient conditions for which the limiting shape of the station distribution will be the same as the limiting shape of the original posterior. We can kind of understand that when that happens, if if this quantity ends up being linear, asymptotically linear in theta, then we will obtain the correct shape. We kind of formally lay down conditions like which relate to sort of LAN expansion conditions under which this happens. So one of the conditions is the classical DQM, which is sufficient for LAN property, yielding sort of asymptotic normality to posterior, like a BBM theorem in parametric models. So this is a very typical assumption. And on top of that, we need to assume like a version of that assumption for p hat. So this is for the original likelihood, this is for the p hat estimator. And then we have two differences here. We have a little bit slower sort of rate, and then we have convergence in probability. So this would be just a assumption under which we can show that the fixed generator design is going to have the right limiting shape. And if in addition, we can conclude that this quantity u of theta, which is averaged out here, if that kind of averages out to 0, then we will have a correct location as well. So this will be the two sufficient conditions for getting the right limiting shape. So let's talk a little bit more about theory. I don't want to overemphasize it, but I think it's still interesting to understand the implications of the exponential tilt and what is it what we are actually computing and how fast we are learning about theta. So the station distribution in both the fixed and random generator design is exponentially tilted original posterior, right? And now we kind of thought about, well, we are learning about theta naught, and in Bayesian parametrics, we quantify the speed of learning in terms of rate of convergence of the posterior around the truth. So we were just kind of curious, how can we quantify the speed of learning here now that we have this exponential tilt? So we thought about two ways of thinking about it. So one way would be, well, we have this exponential tilt. We can maybe assume that it's kind of like part of the prior, and we could regard this quantity as a kind of empirical base prior, which depends on the data, because u of theta depends on data, right? The classifier depends on data. So we could like reframe this quantity as a actual posterior under kind of a relearned prior and obtain a concentration around the truth. And that concentration rate depends on the speed at which we are, the discriminator is like the rate of convergence of the discriminator in some sense, which is expected, because if the discriminator is close to the oracle one, then we are basically, the u of theta will be 0, and then we have basically the right object. So we kind of did that just to understand the rate of convergence. And then we thought, well, maybe for the fixed generator design, asking how fast the posterior concentrates around the truth is perhaps not necessarily right question, because the things can be biased, and we know that maybe the posterior will be concentrating elsewhere, not necessarily around theta naught, because of that non-vanishing bias. So especially for the fixed design, we thought it would be more interesting to understand where is it concentrating. And it's kind of obvious when you think about this quantity as a posterior under model misspecification, where we hide the exponential tilt not inside of the prior, but we hide it inside of the likelihood. So we regard this quantity as kind of like a misspecified likelihood. And then under that scenario, we know that posterior will be kind of shrinking around the KL projection. So we kind of know that the bias that we may expect in the fixed generator design will be kind of the distance between the theta star and theta naught. So that's more of a, I guess, more realistic reflection of the asymptotic behavior, things concentrating around KL projection. So just to complete the story here, here we have just a quantification of the convergence rate. The first one is around the truth, where the rate depends on the rate of the original posterior, inflated by the rate of convergence of the U. So U is the residual, right, where we're looking at the kind of a distance between the oracle discriminator and the estimated discriminator. And as we expect, should be close to zero, right? But the rate at which it kind of converges, it's going to affect the learning rate around the truth. Obviously, this can, this kind of distance from the truth is kind of maybe quite large if this quantity is not very small. So the second type of result is just basically applying standard Bayesian non-parametric tools for model misspecification, in which case we can conclude things converging around the KL projection at a certain rate. And we can also conclude asymptotic normality, where the posterior will be concentrating around, again, mean, which depends on the KL projection, and variance, which also depends on the KL projection. So in this case, the variance under certain conditions which are weaker than the ones I gave you previously, the variance may not be necessarily the correct variance because of this kind of misspecified case. So this condition is a little bit weaker than the one we had before. If we had assumed the DQMP, then the conclusion was that the variances will be actually the same. But these are just kind of asymptotic, nuances. But we like to think that there is a hope for some sort of reasonable limiting shape, even though in specified cases, the credible sets may not be necessarily having great frequency properties, but that's for another story for another time. I don't think that's really the main key of the paper. So I want to now present some examples that we tried. One of them is a kind of a toy example of IID experiment from a Gaussian location scale model. So we have two unknown parameters. We assigned the typical conjugate priors. Obviously, we know the posterior, so this should be pretty straightforward comparison. For the discriminator, we decided to use logistic regression with quadratic terms, because that's kind of close to the oracle discriminator. We generate 500 samples. Also, the fake data will be 500. And we obtain the following. So the first panel is more of a diagnostic, and then the second panel is the results. So the first panel portrays the likelihood ratio estimator, or the likelihood estimator, log likelihood. So under the assumptions that I presented a few slides back, we know that the log likelihood should be, in a fixed design, should have the correct scale and perhaps some bias. So the location we would expect for the fixed design to be a little bit shifted. And that's kind of what we see here, where the truth is the orange curve and then the blue curve is the estimated one. You can see that the kind of amount of variance is kind of, the spread looks similar, but it's a little shifted due to the bias term. For the random algorithm, the likelihood estimator will be kind of wiggly because we are refreshing the latent data, so it's not a smooth curve. But we can see that perhaps it's kind of centered around the right place. It's going to have increased variance. So it's now we can see the bias variance trade-off of those two. And below is the histograms of the posterior reconstruction for the parameter mean, the mean parameter. The next slide is about the variance. So the fixed generator is perhaps producing some samples which are a little shifted. The random generator may produce samples which are a little bit more spread out. And the debiasing may improve the quality of the fixed generator by kind of moving those samples more to the area of high posterior density. So the true posterior density is the orange curve. The bias variance trade-off can be maybe more visible from the variance. So we did the same for plots for the variance here. Again, the likelihood estimator might be shifted, and the fixed generator might really be yielding posterior samples which are kind of shifted as well. And this is where the debiasing might improve the quality of the fixed generator. So again, like we like to think that the fixed generator might be okay to deploy in some instances, but sometimes we can do even better doing the debias. So I believe that right now I have roughly 20 minutes. So I would like to present a few examples. And the first one is a situation where we thought that pseudo-marginal Metropolis-Hastings is feasible to deploy. And it would be a nice model where we can actually compute the posterior itself. So we can run the exact Metropolis-Hastings, and we can make comparisons with the pseudo-marginal technique, because here we have a way of doing that. And then in the second example, I'm making comparisons with ABC. So this first example is all about making comparisons with pseudo-marginal. So the CRR model is part of the Heston model for modeling sort of instantaneous variances. And it's prescribed by the stochastic differential equation, where we have some sort of a mean parameters, so drift parameters, and variance parameter. And this model is kind of fun to work with because we can actually obtain the likelihood of the transition function is kind of available in a closed form. So that's why, you know, this is kind of interesting test case, because we can make comparisons with the actual truth. And what's kind of challenging here is that we have a continuous time process, and we want to make Bayesian inference based on discretization. So we obtain discretization of this process, and we want to perform Bayesian inference. So the data points that we observe the process at these data points, TJ, which are kind of a grid of values, which depends on this kind of distance, delta, sorry. So we assign some reasonable priors. So these priors were actually taken from one research article that I'm actually blanking on, but these priors have been kind of reasonable choices. And then what we do is we generate 100 time series. So it's not only just one time series, but 100 of length 500. And discretization is at the time point 1. And the transition function for this process is actually known. So it's like non-central chi-square distribution, something like that. So we can implement exact Metropolis-Hastings. Okay, and then we thought, well, it would be only fair to try implementing some other techniques, right? So the pseudo-marginal is feasible here. The trick here is to kind of regard the observations in between two time points as kind of latent data. And then we can approximate the likelihood by sampling this latent data, right, in between those discretized points, and then obtaining the likelihood from sort of kind of sampling these latent variables and constructing the likelihood from these transition functions. So, you know, the reason why I'm kind of showing these equations is not necessarily that I want to explain them, but I want to illustrate that implementation of the pseudo-marginal technique is rather elaborate. So one has to choose how many latent variables, right? Because we have the interval in between those discretized, like observed time points. We need to decide, okay, what is going to be the granularity of the latent data, right? And the granularity is m, and n would be the number of those kind of samples of these latent variables. And there have been some theoretical arguments that in order for this method to work well, we need at least m squared of these kind of samples of these latent processes between. So we cannot do that as a fact and implemented different versions for variant NMM, and it takes time. So the conclusion was that it can be done. It's not necessarily straightforward to implement, but it can be done, but it can be also quite slow. So here there are these two numbers, m and n, that may appear later on those plots. So just remember that m is the granularity of the discretization of the latent variables. So yeah, let's take a look at some comparisons. So these are plots of the estimated log likelihood. The exact one is the black curve. And then the top panel corresponds to the pseudo-marginal. I'm using one particular implementation of the pseudo-marginal called MCWM, Metropolis, Monte Carlo within Metropolis. So that's not the state of the art, I guess. It's not the most, I guess, elaborate version of the pseudo-marginal, but it's the simplest one to implement. We also know that this method does not have the correct stationary distribution. So our method, in theory, right, the fixed design also doesn't have correct stationary distribution. So we felt like comparing those two might be kind of interesting. So there's definitely other versions of the pseudo-marginal we could have done, but it was already kind of quite elaborate to implement this one. So for now, we have just this method. And we try different m. So m is the number of latent variables we have to sample in between those data points. So it's 2 and 5, and then n would be square of that. And we can see that as we increase m, we are getting kind of closer to the truth, right? So the likelihood is kind of is kind of concentrating, say, around the MLE, right? So the shape is kind of, it's in the right ballpark. For the other technique, for the Metropolis, for the classification-based log likelihood, we considered the fixed design, random design, and we also averaged out the fixed design, say 5 times, just to see what happens, you know, if you kind of try to stabilize it, reduce the variance by averaging many fixed sort of realizations. So that kind of helps smooth it out. You may also notice that here the fixed curve is not smooth, while previously it's supposed to be smooth. It's because the computation here is based on classification, logistic regression, which uses cross-validation. So there's some randomness introduced there. So that's why we don't have entirely smooth curves. But the point here is that these estimated classification-based estimators are kind of shaped around the true value, which is in this case the red curve. And they seem to have, you know, similar shape, and definitely the location is kind of similar as well. So we are getting something, you know, the classification-based likelihood estimators seem to be kind of yielding, seem to be learning about the unknown parameter, right? So we have 3 parameters, alpha, beta, and sigma. So that's kind of a diagnostic plot. So when I saw these plots, I was kind of more optimistic about implementing the procedure, because then I knew that the estimated likelihood has the information about these parameters. So let's now take a look at some posterior samples. So here, the exact curve, the exact posterior is the orange. And then we have the green and violet or blue is the Metropolis-Hastings with, I believe, yes, right. So with, yes. So this would be the fixed and random version. And I think that at some point we consider also fixed averaged out over 5 replications. But here I'm seeing that it's random with 5 replications. So I'm a little bit not sure if it's actually the label is correct. But let's say that the kind of stabilization, if we average out over, say, 5 replications, that helps reduce the variance, and in this case it helped the reconstruction. So there is still some sort of a bias here, but compared to the, say, the marginal, which took considerably more time, I think that this with m equals 5 was in a matter of just something like within many hours. Well, this took considerably less time. So here we can see that the reconstructions are somewhat similar, but what was concerning was that for these sort of marginal, when we look at the 95% credible interval, after having run the procedure for many hours, that excluded the true value. So that was kind of concerning. But you can see that, in terms of the kind of bias variance trade-off, there might be some similar considerations here, where we are getting something reasonable. We are in the right ballpark, but the sort of marginal may have failed at estimating the variance because it was quite far from the original posterior. So that was a demonstration where pseudo-marginal can be applied, can be implemented. It may take a while. It may, not be straightforward to implement. It can be done. Then we thought about some situations where perhaps the implementation of the pseudo-marginal may not be as straightforward. And I thought that perhaps one of those cases would be the Vodka Volterra model, which people have used for ABC demonstrations. But I thought about whether we could implement the pseudo-marginal, but I'm not entirely sure. So I like to think that this would be an example where the pseudo-marginal is far from straightforward, if at all possible. And the model is describing population evolutions of two populations of predators and prey, which may evolve over time. And the model is prescribed through ODEs, so ordinary differential equations. The model can be simulated from. So you could think of the model as being defined as like there's this underlying differential equations, but what we can do is we can simulate from like realizations around the solution to these ODEs. And the ODEs depend on 4 parameters which determine the rate at which the predator is born, the rate at which the predators die, and the rate at which the prey is born, and the rate at which the prey die. So we have these 4 parameters. And it's kind of interesting to deploy the kind of plain ABC. We haven't really gone overboard here looking at some fancy versions of ABC. So we just did what people have done in the literature, looking at sort of summary statistic-based ABC. And what's kind of cool about this type of model is that we obtain very different trajectories if we shift the parameters a little bit. So the evolutions of the populations can look very differently depending on how we choose these. And there's going to be a small range of parameters which give certain oscillation behavior. And that's kind of what we are after. We like to think that the truth is the kind of oscillating behavior. And if we depart from, like, if you consider different parameter values, you may obtain something different, where maybe the population of prey may take over if the predators die out, right? So there could be this kind of explosive behavior in one direction. We could have also sort of predators slowly dying once the prey population dies out. So you can imagine very different trajectories, and that creates hope that if we do classification, feeding in these trajectories into a classifier, the classifier might be able to tell pretty accurately, this type of shape from this type of shape. So we believe that the classification-based approach in this type of data is particularly useful because the classifier should be able to tell apart these very different shapes. So the range of parameters we are going to be looking at is mostly in the simulation. We will be assuming this kind of oscillatory behavior. We will have sort of 20 time units, but again, the process is observed at these kind of different time points. So there's going to be 200 data points up to the time period of 20 units. And we'll start the process at this initial value, and these are the true parameter values we want to estimate, which kind of seem to yield this oscillatory behavior. So these are the parameters we wanna recover. And we kind of considered, again, first plotting the log likelihood estimator from the classification. So we want to see the likelihood to be peaked around the true values, and that's kind of what we indeed see. So what we also see is that the likelihood might be quite sharply peaked around these true values, because if we shift the parameters a little bit, we get very different trajectories, right? So there's a reason to believe that the likelihood might be sharply peaked. And indeed, from the classification, we were able to learn about those parameters. So here we have a slice which depends on theta2, the second parameter. We can see the estimator being peaked around the truth. So that's kind of comforting to see that we are learning about that parameter. We tried something similar using the ABC tolerance level. So just plotting it, keeping all the parameters fixed at the true value, and then varying second parameter. And we can see that ABC tolerance is also kind of has a minimum around the truth. But what was kind of interesting is we tried like maybe averaged ABC tolerance over, over several fake data realizations, and that seemed to be yielding more stable tolerance, which is closer to, whose minimum is closer to the true value. But it's kind of nice to see that ABC is also kind of learning about its parameter, because the tolerance has a minimal value around the truth. So that was also really good news. So we tried the plain ABC using summary statistics, and these were like a mean, variance, liked correlations and cross correlations of the series. That's what people have considered in the past. So we've done that. But before I show you the results, I also want to show you two-dimensional plots. So this is just one-dimensional, where we look at the likelihood estimator as a function of theta2. We did also two-dimensional plots. So this kind of illustrates the spikiness of the likelihood. And it also illustrates that if we have a kind of a flat prior over kind of wide domain, maybe ABC might take a little while to find these spikes, right? So we kind of narrow down the area for the ABC, and we kind of narrow down the prior for ABC, not from 0 to 1, but somewhere smaller for theta1 and theta4, just because we know that the likelihood is going to be kind of very concentrated in a small area. So we kind of narrow down the prior to these two domains for the two parameters, and we run ABC for 10,000 iterations, and it appears that maybe regarding these two parameters we are learning with ABC, but perhaps the summary statistics were not good enough to identify theta2 and theta3. So I initially thought that's maybe just because the prior is too vague, so we have to maybe run it for longer. I think this is based on 1%. Okay, so the upper panel has the top 100 samples out of 10,000. So the second panel is top 1,000 samples out of 100,000. And we are improving learning about theta1, theta4, but for theta2 and theta3, the summary statistics were probably just not good enough. So, okay, we could have maybe tried something else, but maybe there is some other summary statistics that could work. Interestingly, for the Metropolis-Hastings, the implementation seemed to have yielded reconstructions for theta2, theta3, even the first two parameters, the other two parameters, which seem to be concentrating around the truth. So we seem to be getting some reasonable distributions. These are trace plots after 10,000 iterations. And what's kind of interesting is to take a look at those sort of credible intervals. So we look at 95% credible intervals, lower and upper. And the first column is the mean. So the mean is very close to the truth for the Metropolis-Hastings. And the credible intervals are quite narrow, and they cover, sorry, this keeps happening. They seem to sort of include the truth, right? So compared to the ABC, which seems to yield much wider intervals, and perhaps the estimator, the posterior mean, is not as close to the truth. So in this case, we have concluded that this plain ABC may not have really worked as well. We also have noticed that if we don't initialize the Metropolis-Hastings in a good place, it may take a long time for the burn-in. So what we've decided to do is perhaps combine the two by running ABC for a while and then getting the posterior means and then initialize there. So there's a way of speeding up the convergence of Metropolis-Hastings. So that's kind of the second demonstration I had, which illustrates that this technique can be deployed in situations where pseudo-marginal might not be available, and in situations where poor choice of ABC statistics might hamper ABC inference. So I think it's a kind of viable alternative to those two techniques. And the last example I have, I know there was a question, but I'm happy to skip this last example. We know that ABC may not work for model choice if the summary statistics are not right. So if you take one of those kind of quintessential examples, you can show that indeed ABC may fail for model comparisons by getting base factors which are close to 1, which is equivalent to coin flip in between, like when we compare two models. So the Metropolis-Hastings in this case with discriminator, which was like a logistic regression quadratic, yielded kind of some base factors which are more reasonable. So that could be another sort of argument that maybe this technique will be less because it doesn't rely on summary statistics. It might be less prone to. It might be well suited for model comparisons. So with that, I would like to wrap it up because we're kind of running out of time. So I would like to also acknowledge my student Yuxi Wang, who's been trying computations and simulations, and she's also working on a more kind of ABC like version of this approach. So I would like to thank you for your attention, and I'm happy to take any questions.
Okay, brilliant. Thank you very much, Veronica. Do we have any questions from the audience? So the last thing in the chat was just a comment, somebody saying thank you for the talk, but they had to leave. Do we have any questions from anybody else in the audience? Okay, so something in the chat. Yes, comment from Umberto in the chat. Umberto, do you want to unmute? And...
Yeah, I think it's nicer to ask straight away. Thanks for this very nice talk. Just a small comment on since you consider this Vodka Volterra example and some of the ABC inference was not super satisfactory. So there is a nice paper by Darren Wilkinson and Jamie Owen and Colin Gillespie. So they did use ABC to initialize a pseudo-marginal method, and you can maybe look at the results for comparison. I think they use a 3-reaction Vodka Volterra. You use a 4-reaction Vodka Volterra, which is, maybe it's a bit more difficult to infer than their case. So maybe that paper could be useful for if you want to simplify a little bit the scenario.
That's an excellent suggestion. So I'm going to definitely look into it. And I'm really happy that people have used ABC to initialize other computations because, yeah, it can really help. So thank you for the suggestion.
So Veronica, I wanted to ask, do you think there's much advantage or disadvantage to using a neural network discriminator rather than logistic regression?
So, we started this project hoping that the neural networks would be, it's really the classifier we want to use, and it's flexible. It may take longer, so we have to refit the classifier at every step. So we have seen that the neural networks can, take a while to tune, depending on the specific example. So I believe that there is potential, but somehow using the logistic regression or something simpler, it speeds up the computation and it may be satisfactory. So it will be interesting to see whether the deep learning really improves the accuracy. It won't improve the computation speed, but I'm hopeful. I'm hopeful that that's the case, but yeah, I don't have necessarily. We have tried the neural networks on other models, and it works, but it's, again, like, I like to use simpler techniques when I can. So the logistics seem to have worked really well on those 2 examples that we just saw. but definitely something to look into.
Okay, thank you. And unless anybody else wants to jump in with a question, I had one final thing, which was, do you think any of your theory could carry back to GANs?
So there's definitely part of theory, the convergence of the discriminator, which has been actually which has been used to so the convergence of the discriminator, that part is kind of can be deployed to gain some insights about GANs. Yeah, I don't have any other necessary any other suggestion, but part of that theory definitely applies to GANs.
Okay, thank you. And we had a question in the chat from Andred Straka. Would you like to unmute and ask your question?
Yes, thanks. Basically, just a small question. I think it was a great talk. I think you were mentioning combinations, possible combinations of the fixed and random generator. Have you considered those possibilities, probably some optimization, and to what extent can this be combined?
That's a good idea to think about combining them in one run, right? Maybe, yeah, we haven't really, we run them separately and then we kind of debias them at the end. But we haven't really considered alternatives such as like combining them in one run, or using something like the correlated pseudo-marginal where we recycle the latent variables or things like that. So I think that there's many more possibilities to try, but we haven't, the only combination we tried was the debiasing one at the end.
Thanks.
Okay, so unless anybody would like to quickly ask any final questions, I will draw this to an end. So thank you very much again, Veronica. Thanks for getting up so early at your time to speak to us.
Thank you.
But thank you very much for your attention and for the great questions.
Okay, so I'll just stop the recording.